Hi, I'm Bob Pryor, and I'm talking to you today about trigonometric identities. We're talking about how the trig functions interact with each other. Let's start with the reciprocal identities. We've seen these before. Secant theta is 1 over cosine theta. And it makes sense then that cosine theta is 1 over secant theta. 1 over something means the reciprocal of. The thing is about these identities is we can write them one way, as you've seen, but we can also write them kind of in the reverse order. For example, we see secant theta equals 1 over cosine theta, but we can also write that as 1 over cosine theta equals secant theta. And likewise, cosine theta is 1 over secant theta, so 1 over secant theta is equal to cosine theta. We also see our reciprocal identities for cosecant and for sine. They're reciprocals of each other. So cosecant is 1 over sine theta. And remember, 1 over something means the reciprocal of. We can also write that in the reverse order. 1 over sine theta equals cosecant theta. And I can do this for all of the identities. Of course, we also have sine theta is 1 over cosecant theta. We also have the reciprocal identities for cotangent and tangent. So let's kind of put this into action. If we know, for example, that cosine of theta is 2/7, well then secant theta simply must be the reciprocal 7 over 2, or 7/2. And if sine theta is 1/5, well then cosecant theta, we might first write it as 5 over 1, but we should then simplify that to just 5. In example C, notice that tangent is negative. Well, that means the reciprocal will also be negative, so cotangent will be a negative number. And then we flip the fraction. Negative square root of 5 over 2. Example D, cosecant is square root of 7 over 2. When we take its reciprocal, we get 2 over square root of 7. But we must rationalize the denominator. So here we'll multiply by radical 7 over radical 7. And what we get is 2 root 7 over 7. What's next? The ratio identities. This is where we compare sine and cosine in a fraction. Sine theta over cosine theta. That's what tangent theta is. And cotangent theta is its reciprocal, cosine theta over sine theta. So why is it that tangent theta is sine theta over cosine theta? To discover why tangent theta is sine theta over cosine theta, let's first start with our definition. Sine theta is y over r, cosine theta is x over r. Then when we have the fraction sine over cosine, that's y over r over x over r, which we can then rewrite as multiplication, y over r times r over x. The r's divide out, and we get just y over x. And that is actually the definition of tangent theta. So what we see here is that sine theta over cosine theta is tangent theta, and of course that means that tangent theta is sine over cosine. So let's put this into action with these numbers. Cosine theta is 3/4, sine theta is radical 7 over 4, but we start by recognizing tangent theta is sine over cosine. And we write that as radical 7 over 4 for sine, and then 3 over 4 for cosine. And when we write this as multiplication, we see that, nice, the 4's divide out. And we get simply square root of 7 over 3. I'll let you do the cotangent of theta yourself. All right. The square of a trigonometric function. For example, sine theta times sine theta. Well, that's sine squared theta, but the way we might write that at first is sine of theta, the whole thing being squared. However, in trigonometry, we abbreviate that by putting the square on the trig function. We call it sine squared theta, and we are not squaring the angle, we're squaring the function. So sine squared theta. It's important to recognize that difference. So let's consider, for example, where sine of theta is 3/5. Then sine squared theta is simply 3/5 quantity squared. And when we multiply that out, that's 9/25. Let's take a look at these two examples. First of all, cosine of theta is 2/3, so cosine squared theta is 2/3 quantity squared. And that's 4/9. A little more challenging is when we've got a square root. So tangent theta is 5 square root of 2/6. When we square it, we square everything. And that means we'll square the 5 and get 25. Square the square root of 2, we get 2. And square the 6, we get 36. We can divide out 2 from the 2 and 36, get 1/18. And that becomes 25/18. Okay, now we're going to talk about a full group of identities called Pythagorean identities. And there are several, and they are based on the Pythagorean theorem. We're going to learn how these interact with each other by first reminding ourselves of the identities that we already know. Sine theta is y/r, cosine of theta is x/r, and x squared plus y squared equals r squared, which is where we're going to start. Now what we're going to do first is we're going to divide each side by r squared, and then we can separate the left side into two fractions, x squared over r squared plus y squared over r squared. On the right side, that just becomes 1. Now x squared over r squared can be thought of as the quantity x over r, that whole quantity squared, and then same thing, y over r quantity squared, and it's still equal to 1, of course. But x over r, that's cosine theta. So x over r squared is cosine squared theta, and y over r squared is sine squared theta. And this gets us our most basic Pythagorean identity, in which all other Pythagorean identities are built. Let's see how we can use this basic identity, cosine squared theta plus sine squared theta equals 1, to develop some other identities. We'll start by solving this basic equation for cosine squared theta. That means, of course, we want to get cosine squared theta alone on the left side. And the way to do that is to simply subtract sine squared theta from each side. And when we do, we get cosine squared theta all by itself on the left, and on the right side equals 1 minus sine squared theta. This is another Pythagorean identity, and you'll want to know it well. One thing about identities, and this is very true for Pythagorean identities, we can rewrite them in the other direction. So 1 minus sine squared theta equals cosine squared theta. Now you want to become very familiar with these Pythagorean identities. Here's another one. We're going to solve this time for sine squared theta by subtracting away cosine squared theta from each side. As we do, we'll be left with just sine squared theta on the left, and it will equal 1 minus cosine squared theta. Again, you want to be able to read these forward and backward. So sine squared theta is 1 minus cosine squared theta, and then we could also write that as 1 minus cosine squared theta equals sine squared theta, backwards and forwards. We can also take the square root of these identities. So we have this new one, cosine squared theta is 1 minus sine squared theta. We take the square root of each side, we will develop another form of a Pythagorean identity. We'll say cosine theta is equal to, remember now, plus or minus the square root of 1 minus sine squared theta. That plus or minus comes into play depending upon where theta is in which quadrant. And if theta is in quadrants 2 or 3, cosine will be negative. We can do the same thing for sine theta. Sine theta is plus or minus the square root of 1 minus cosine squared theta. And again, sine theta would be positive if theta is in quadrants 1 or 2, and negative if theta is in quadrants 3 or 4. Let's put this into action by working with the cosine theta identity. We're going to find cosine theta with given information that we know that sine of theta is negative 2 root 6 over 7, and, very important, that theta terminates in quadrant 4. Being in quadrant 4 means the cosine value is positive. So, when we consider the plus or minus portion of this formula, we use the plus sign here, the positive, because it's in quadrant 4. If theta had been in quadrant 2 or quadrant 3, our cosine would be a negative square root. Again, it's positive square root. So, 1 minus the sine squared. Well, sine is a whole quantity, negative 2 radical 6 over 7 squared. We now use the order of operations to simplify this. 1 minus. When we square those, we get 4 times 6 over 49. 4 times 6, of course, 24, but what we're going to do is get common denominators of 49. So 1 is 49 over 49, minus 24 over 49, and that conveniently becomes the square root of 25 over 49, and that's a perfect square fraction, 5/7. And it's positive, again, because theta is in quadrant 4. Let's see what's next. So, as I mentioned earlier, we have a lot of Pythagorean identities, and we have another Pythagorean identity that involves tangent and secant. And the way we find this is we start with our original Pythagorean identity, cosine squared theta plus sine squared theta equals 1. This time, though, what we're going to do is divide each side, or in this case, we'll just go straight to dividing each term by cosine squared theta. As we do, we'll create another Pythagorean identity. Cosine squared theta over cosine squared theta is 1 plus sine squared theta over cosine squared theta. That's sine over cosine is tangent squared theta. And 1 over cosine squared theta is secant squared theta. So that's a new identity. One more Pythagorean identity for you to memorize. Yay! We can do the same thing by taking the original basic Pythagorean identity, the cosine squared theta plus sine squared theta equals 1, and divide it now by sine squared theta, each side, each term. We'll generate one more Pythagorean identity. The one that you need to be most familiar with is the original, the cosine squared theta plus sine squared theta equals 1. As you can see, all others come from that, and I'll let you finish that yourself. So let's now find an identity for just tangent squared theta, a Pythagorean identity. Of course, we start with the original that we just developed, 1 plus tangent squared theta equals secant squared theta, and this time we'll subtract 1 from each side, because we're solving for tangent squared theta. And this will give us tangent squared theta on the left, and on the right side, secant squared theta minus 1. Again, one more Pythagorean identity. But if you know the basic one, you can generate all of the others. So here are all 5 Pythagorean identities. What's not included here are the square roots that we talked about a little bit ago. They aren't used as often. These are more common to use. In fact, it's the sine and cosine that's the most common. And as a reminder, we can write these identities in a different order. So where cosine squared is equal to 1 minus sine squared, 1 minus sine squared theta can equal cosine squared theta. 1 minus cosine squared theta equals sine squared theta. Become very familiar with each of these. Well, I hope this has been enjoyable. I've had fun. See you later.